Hey Maddie, so I thought this problem was really cool, and I guess I thought it was cool because I don't really work with energy too much, and I'm trying to actively get better at it, and I feel like this problem helped me a little bit. So I was like, wow, that's cool, and I immediately thought of you, and I was like, she'd probably think this is cool too. So it kind of led to the whole idea of the video, but anyway, um, 225 is asking what is the force on the inclined track on the block at the bottom? So at the bottom, we have a flat point right here, right? So technically our block would be laying like that. And that means that the only forces acting on the block would be the normal force and the force of gravity. Because, yeah, that's like, it's at that instant right there. And it's asking for the point at that instant at point A. So the sum of the forces at point A would be just equal to n minus mg equal to 0. Because it's in equilibrium in the y direction, it is no longer moving up or moving down. So yeah, that's pretty much it. The force on the track on the force of the track on the block at point B. Now point B gets a little more difficult because now we don't have a necessarily flat area to be working with. So there's this curve right here. And in introductory mechanics, we learned that any time that an object goes through circular motion, it's experiencing both its velocity here, or acceleration, or whatever it is experiencing, and it also experiences centripetal acceleration. So if we were to apply that to our diagram, which our diagram is just kind of going this way, so we would have the normal force, which is also at that point equal to centripetal acceleration, right? And in introductory mechanics, we learned that the centripetal acceleration is equal to v squared over r, over the radius. So at this point, the force acting on it would be the normal force, which is also the same as centripetal acceleration. And since gravity always acts downward, it's actually in reference to this angle right here, to the angle between the normal force and the force of gravity. So kind of like how Dr. Basurto was talking about when things are, or when things apply torque. There's no torque applied if both of the unit vectors of our direction for our vectors are in the same, basically like in the same line. So then these would balance out if the forces had the same magnitude, or if they're unit vectors, they cancel out. So since in our problem it's kind of like upward and we have downward, right? Because that's how gravity is here. So let me draw it a little better. So our normal force would be acting that way, and the force of gravity would be acting downward, giving us an angle theta here. So then we can write as the forces in the b direction is equal to n minus mg, and then we can't forget the cosine because that's technically what helps balance out our direction. So n minus mg cosine theta. That would pretty much be equal to the forces in this direction. And it also is equal to the centripetal acceleration because that's technically the only thing going on in the movement. It's going through the curve, which gives it a centripetal acceleration. Since it's not moving up or down, um, n minus mg still equals just centripetal acceleration and not 0 this time. And that pretty much explains part B. At what speed does the block leave the track? This one's where we start getting into energy and it gets really fun. Let's see if I can work through this first try. Um, okay, so what do we know about the block at point B? Well, at point B, well, first of all, let's say energy. Oh my God, what was that? Energy is conserved the whole time. Energy is conserved. It's amazing to work with conservation laws. Um, so we can say that the energy at point B is equal to the energy at point A. And that makes the problem a million times easier because the energy at point A, it's on a flat point, like right here at A. So, and at that instant, it stops gaining kinetic energy. It doesn't have any kinetic energy because, like, the instant it starts moving up the track, it starts losing kinetic energy. And in vibrations and waves, we learned that the instant that something starts losing kinetic energy, it obviously stops gaining it. So technically, kinetic energy at that point is equal to zero. And all that's left now is our potential energy because the block has no more kinetic energy to be going through, but it has enough potential energy, or it gets potential energy because of this incline. So then we can write that the energy in B is equal to the energy in A, which is just mgh. So that sets up our first variable. And now we're actually dealing with it at point B. At point B, it already started the incline. So we're here. And at point B, since we're moving, we do have kinetic energy. So that would be our first part. We can define energy as T plus U. So we have T plus U equals mgh. And then, well, what's our T? T is pretty easy. It's usually always equal to half mv squared. And then our potential energy, which is just like how much the block is going to rise before it like shoots off the ramp over here. So that would just be equal to mgh. I guess we could say mgy. Why not? Because that would be just like our height basically. So yh, same things pretty much. And then that would both be equal to mgh. So pretty much from here we can solve a lot of things. It's asking, what is it asking for us again? Ah, yes, at what speed does the block leave the track? Okay, so pretty much we just solve for here. So I'm gonna throw in one more formula that makes this a little more helpful, which is y is equal to the height, or wherever we are, at point 1. Sorry, in my other notes I was using like point 1 and point 2. So the height, sorry. Yeah, forget. Okay, let me restart. So the height is equal to, basically this is our formula to find the height of any circle at any given point. So if we wanted to find the height here, it would just be the radius times 1 minus cosine theta. So we're also given that theta here is equal to 45 degrees. So our height is equal to r 1 minus 1 over the square root of 2, because cosine 45 is equal to 1 over root 2. So this would be our equation for y, right? And I got a little confused with my notation because I used h1 instead of y. I for some reason like to use the same variables and not switch, and it makes things 1,000 times more confusing. So I always recommend switch whenever you can, just to help identify variables a little better. But this is our y. So our height of the circle is given by this equation, which just basically gives the height of any circle at any given angle theta. So we can set this up as half mv squared plus mg r 1 minus 1 over root 2 is equal to mgh. And basically from here we just solve for v squared. That's what gives us our speed. So v squared, since it's velocity, and it would technically v squared is equal to v dot v, which when you multiply two vectors you end up getting the basically just the magnitude squared. So v squared is equal to 2 mgh minus mg r 1 minus 1 over the square root of 2. And that's pretty much our speed equation. You can also, oh, I forgot I have an m here still, so this cancels out these m's. So then we get v squared equals 2gh minus g r 1 minus 1 over the square root of 2. That's pretty much our equation for speed. If you want, I think in the book he factored it out, so if it wanted to look exactly like the book, h minus r 1 minus 1 over the square root of 2. I don't know why I did h again. This is supposed to be r. Anyway, that's exactly what it looks like in the book, but that's the derivation to get there, pretty much. Just set up the equation in terms of energy, and then solve for the speed. It's pretty cool. I like that, and I think it's so interesting that just knowing where the object is, or where it could be, you can immediately tell the speed from it. That's so cool. It's like a predecessor to the Lagrangian right here. It would, like, I thought about solving this with the Lagrangian because I was like, why would I need to work with 2 coordinates when I could just work with 1? But it's a process, honestly. But yeah, that would technically be our B. And then, let's see, what is C asking? Oh, actually, that's C. What speed does the block leave the track? C. And how far away from point A does the block land on level ground? Honestly, I'm going to skip E because I don't want to sketch the potential energy. If you ever sketch a potential energy, usually most of the time, the graph looks exactly like it would in the curve. I don't know if you've ever graphed anything like from potential energy, but it looks exactly like it would as if it were like a racetrack. Yeah, it's crazy. But anyway, I digress. How far away from point A does the black land on level ground? This one's fun because it honestly just becomes a projectile motion problem. So we can just basically set up our equations of motion. We have mx double dot is equal to 0, which would give us x double dot equals 0. Integrating one time, we would get x dot equals to a constant. And then our constant is just basically, since x dot is equal to v, so we would just get v. But since we are also in a circular path, we have to also factor in the cosine theta. And it might also keep in mind, I forgot this and I was running around in circles for like 15-20 minutes yesterday. Cosine theta is equal to 1 over the square root of 2, and so is sine theta. It's equal to 1 over the square root of 2, because theta equals 45 degrees. I honestly don't like that. Was that pi over 4? Yeah, I think that's pi over 4. If I'm wrong, that would be horrible. Yeah, because pi over 2 would be 90. I think that's pi over 4. I hope so. Anyway, so our constant is equal to v cosine theta. So our equation of motion now becomes x dot is equal to v naught cosine theta. And that's just initial velocity. And then integrating it one more time, we would get v naught t cosine theta. And that pretty much sets up our first equation of motion. So since we also have, oh, my bad, I forgot the arbitrary constant here. So whenever you integrate, there's always another arbitrary constant, C2. C2 in this case would just be equal to, so if we zero everything out, the V naught T, the T becomes 0, because we're doing x of 0. So then this cancels out. We have cosine theta plus C over square root of 2 plus C, not C over square root of 2, sorry. So then our constant would just be x naught is equal to C. Cosine theta also goes away. So our total equation of motion now becomes x is equal to V naught T cosine theta plus whatever position we were starting at. And now for y, we have my double dot is equal to minus g minus mg. And setting it up, taking away the m, y double dot equals minus g, y dot equals minus gt plus c. And then we do the same thing. We zero out our y dot, gt. This becomes 0 because we're doing g of 0 plus c. So this would mean that our c is actually just equal to our initial velocity. In the y direction, since our projectile is also coming from the same origin, from x and y, we can also just write this as our initial velocity, y dot 0. So our equation of motion now becomes y dot is equal to minus gt plus v naught. Again, I also forgot that we're doing it in relation to an angle, so always whenever you're doing it into relation to an angle, your y-axis uses sine theta and your x-axis uses cosine theta. So our full equation of motion becomes v naught sine theta plus v naught sine theta. Then we integrate one more time to get our function of y, which we would get minus half gt squared plus v naught t sine theta plus our second arbitrary constant. Same thing, our second arbitrary constant, once we zero it out, y naught is equal to minus 1/2 g of 0 plus v naught 0 sine theta plus, why did I do 2? It's supposed to be c, sorry, plus c. So this cancels out, and we are just left with y is equal to minus half gt squared plus v naught t sine theta plus whatever our initial position was. And that pretty much derives the equations of motion from there, but it's asking us how far away from the point does it land. So when we're trying to figure out how far away something lands given a projectile motion, basically we need to find out how long the projectile takes to get back to the ground here. And that is only a change in y. So we're looking for y, for t, in the y direction, because it's like how long it takes our projectile motion to hit 0 in the y direction. Usually the way I go about this is I will just write my original equation of motion, y equals minus 1/2 gt squared plus v naught t sine theta plus y naught. And solving for t, we get, let's simplify this a little bit. So since our theta is equal to 1 over the square root of 2, then we get minus 1/2 gt squared plus v naught t over the square root of 2 plus y0. And this right here is a very, very, very beautiful quadratic equation in T. So what we can do to solve for it, you can separate the variables and do all that, or just kind of plug it into the quadratic equation, or yeah, the quadratic formula. So you get negative b, which is v naught t over the square root of 2, negative v naught t, negative b plus minus square root of this squared, I don't know why I'm writing t's, sorry, square root of b squared minus 4 times minus 1/2 a, that's a times c, which is just y0. And this goes all inside the square root. And then all divided by 2, 1/2 gt. And that pretty much solves for our equation of time. And I'm lazy, so what I'm gonna do is set that equal to gamma, right? So once we have our equation for how long, this is the equation for how long it's gonna take the ball to hit the ground in terms of the y direction. So this is basically our time of flight, like how long it's gonna be in the air for. And if I wanted to know how far it goes, so just basically plug this into x of t. And x of t was given to us up here. So we can write, also I'm going to simplify the cosine theta again, because cosine theta is also equal to 1 over the square root of 2, given a pi over 2 axis, pi over 4 axis, sorry. So we have v naught t over the square root of 2 plus x0. And then our projectile would be x of gamma. That's how far it would land, because gamma. So it would just be v naught over the square root of 2 gamma plus x0. And then basically once we're here, we have our equation for time. All we need to do is figure out this x naught. And from polar conversions, x is just equal to r cosine theta, and y is equal to r sine theta. So we have our initial position, so we just have r over the square root of 2, because cosine theta turns into 1 over the square root of 2. So then we just plug that in for our x naught. So our total x of gamma is equal to v naught over the square root of 2 gamma plus r over the square root of 2. And this just basically tells how far our projectile would land. And yep, that pretty much concludes the whole problem. I hope it's understandable and you can go through it. If you have any questions on it, just let me know. It's not that hard of a problem. It was fun to learn. Took me like an hour and a half. But yeah, thanks for coming to my TED Talk, dude. I'll see you later. And then basically once we're here, we have our equation for time. All we need to do is figure out this x naught. And from polar conversions, x is just equal to r cosine theta, and y is equal to r sine theta. So we have our initial position, so we just have r over the square root of 2, because cosine theta turns into 1 over the square root of 2. So then we just plug that in for our x naught, so our total x of gamma is equal to v naught over the square root of 2 gamma plus r over the square root of 2. And this just basically tells how far our projectile would land. And yep, that pretty much concludes the whole problem. I hope it's understandable and you can go through it. If you have any questions on it, just let me know. It's not that hard of a problem. It was fun to learn. Took me like an hour and a half. But yeah, thanks for coming to my TED Talk, dude. I'll see you later.